I'd like to ask Hava to carry on the session. Thank you.
So I have to thank you for the introduction, because that's what I was planning to say. How much it was fun to be part of this excitement and the pleasure to be with all the students that we all were inspired by the energy and the love for science that Rami induced around. And we will dive into the synapse, which was the first step in understanding HPNS, as you will see. So, written in one of the reviews by Rami and some of the students, pressure, like temperature, is one of the fundamental physical variables which constrain living entities. And the study of pressure effect on biological system is motivated by biophysical, environmental, evolutionary, and diving medical reasoning. And I think all of us in the difficult times of the difficult electrophysiological setting under pressure were trying to stick to this motivation and get the power to overcome these bumps on the way. And since pressure per se, not the effect of some gas under pressure, induce HPNS, which is associated with neuronal hyperexcitability, the way that the first works under pressure in Rami's way were trying to look at synapses, the place where neurons contact each other in order to maybe shed some light on the hyperexcitability of the whole brain under these conditions. And what is the synapse? Just a brief introduction. We see here a nerve cell, an axon, and at the end, the nerve terminal. When action potential propagates to the nerve terminal, opening calcium channels, which actually cause exocytosis of these small, tiny vesicles that we see here. And that's cause release of neurotransmitter, which bind receptors in the postsynaptic side. And if this opening conductance for cations, we'll get an excitatory postsynaptic potentials. And in most of the cases, if these are anions, then we'll see inhibitory potential. So in order to reduce the system and try to really look at the single synapse, the first approaches were to look at the neuromuscular junction. This is a simplified model of a synapse. You can see here the vesicles. You can see here the active zone with this black bar. And in the postsynaptic side, at this T-shaped structure, the receptors are located. So exocytosis of its vesicle here will be recorded as an EPSP or EPSC at the postsynaptic side. And the setting that I mostly used was the opener muscle, either in crayfish or lobster or other crustacean. This muscle over here is innervated by a single common exciter neuron that you see here. And here you can see that these are actually two axons, one excitatory and one inhibitory. So it's really easy to travel around here and look for a spot where a synapse is present. And how do we see that there is a synapse there? We can detect these little bumps here, which are spontaneous activity of the synapse and are called miniature excitatory postsynaptic potentials, which help us to detect the synaptic site and also to see the spontaneous activity at the minimal unit of synaptic activity. So we try to do these measurements of the spontaneous over here and the evoked potential here. You see an artifact. You see the delay to the action potential, this little bump here, to arrive to the synaptic terminal, and then this current reflects synaptic release of neurotransmitter and this current that I mentioned before. And then we try to do it under pressure, of course. So how do you do it in pressure? At least these times, you really need a chamber to compress everything into this chamber. And I couldn't bring the one that we had in the lab, but I brought something that is very, very similar to this. Something like this, but really much heavier, and with a lid that is much heavier than this, and you stick everything inside, put the electrodes, and then you try to close it gently, screw it, and It's really difficult. Most of the times it's really frustrating, so then you need the Ramin spirit, and you rest with the Ramin spirit and energy, and then you can go on and do the experiments. So the first set that I brought here are works by Grossman and Kendig. We see here an EPSP, synaptic potential at normal conditions, normal pressure. You put it in under pressure, 100 atmospheres, and that's what you see. Smaller, and the kinetics are changed. You decompress it, and then you see a recovery of the signal, which, if you think about hyperexcitability of the brain, it's really not exactly going directly at the same way. And then they did experiments of repeated stimulation to the nerves, and we see here the classical phenomena, which is the first EPSP at the left. You see that the size is similar to the synaptic potential over here. And the last one in the trend, this is at normal condition, is potentiated. So you see some potentiation, facilitation that we all know that is partially due to changes in calcium in the presynaptic terminal. And this was the first clue. Looking at the left over here, we see the suppression of the response, but some increased facilitation, which indicate for the people that are into this topic that something may change in terms of entrance of calcium through the presynaptic terminal. And they took it further in another collaboration with Colton and Gilman, where they showed at the top, these are traces of normal APSP at normobaric conditions, and then blocking with cadmium or nickel the specific calcium channels and currents, and the additive effect of pressure that we see on these two responses. And then, actually, this was the baseline for my work, and we tried to repeat the experiments with the macro patch clamp technique that enable us to see the action potential arriving to the presynaptic terminal, as I showed before, this first bump, and the EPSP, and at almost 7 megapascal, 70 atmospheres, we see the suppression of the response. At the bottom, just to mention that we try to see also the inhibitory response for the to be short. I will skip this part. But what we try to explain with this method is these variables that are mentioned here. So if the synaptic response is smaller and maybe shorter, what explain it? And the variables that are mentioned at the top, I will just tell a little bit about everyone in the next slide, can explain us what really changed. Are these small vesicles now contain less neurotransmitter, or there is less current, or like more vesicles or less vesicles were released? That's what we try to answer with this set of work. And in order to do it, you need to repeat the recording of these synaptic currents many, many times. And by doing it, first thing that we notice with doing nothing, like not related completely to pressure, it's just that we had two types of synapses. One synapse that we see here on the top, that is what we call low-yield synapse. Usually the synaptic current is small, and we see some cases that there is no synaptic current at all. We have failures of the synapse, so there is no exocytosis of neurotransmitter at all. And the responses, the amplitude of this response are over here in these white circles, vary, which may be due to release of 1 or 2 or 3 vesicles of neurotransmitter. Under pressure, we see a suppression of this synapse, all the black dots that we see here, triangles, and under pressure, we see also many failures of this synapse. So the action potential propagate, but the synapse failed to release a vesicle, exocytose a vesicle of neurotransmitter. And the second type of synapse are the high-yield synapses that we see here. The amplitude is larger to begin with, and under pressure we see this is the average amplitude over here. This is the response. there is a suppression of the number of vesicles that was released, apparently, but we almost see no failures here. So to analyze it, we go back to the basic components of synaptic transmission. Q is the quantal size. What will be the current that is actually we can record in response to a release of a single vesicle of neurotransmitter? M is the quantal content of this synapse, which is the average number of vesicles that were released. And we can calculate the M actually by multiplication of the number of active zones by the probability of each of them to release a vesicle. So we try actually to figure out what are these 4 variables here and what happened to them under conditions of high pressure. Using these equations that are classical in the vesicular release of neurotransmitter and all the theoretical works done by Rachamimov and the colleagues and many other ones. I don't want to mention part because probably I will forget a few of them. We can characterize the synapses, and the high-end synapses can be characterized actually just by the first equation because the release is really massive and we see no failures that, as you see here, are needed for the calculation in the other methods. And the low-yield synapses could be described by actually this equation, and obviously we can use this too. So another characteristic of these 2 types of synapses are that in the high-yield synapse there is almost no spontaneous release of neurotransmitter, while in the low-yield synapse we see the miniature or spontaneous excitatory postsynaptic potentials or currents. So equipped with these equations, we return to the recordings that I showed you before and try to see how these variables are changed. So the first illustration here, actually you see at the left side the number of events. At the y-axis, the amplitude of the signal that I just showed you before. And we look and we count how many events were with each particular amplitude. And that's actually build this histogram here with a mean around the value like about 0.3 nanoamperes in average, which is more or less the quantal content or the average number of vesicles that are released at this site. I will just, in the next step, explain how do we know that this is like the number of how many vesicles are there. Under pressure, we see at the bottom illustration here that all this histogram moved to the left, and now they are distributed around 0.1 nanoampere. And this is like the minimal current that we could get, and for us that was the conclusion that there is a single vesicle that was released over here, and this is the distribution of the currents around the value of a single vesicle, and that means that if here we are around 3, maybe here we have about 3 vesicles that were released. Repeating it many times with the 2 different types of synapses, the low yield and the high yield, we see in all the cases the white is the control, the black is the under pressure, and again here, shift to the left, reduce in the number of vesicles that were released at any activation of the synapse. And the size over here, which is the quantal size, never changed. So there was a size that is corresponding to a release of a single vesicle and the currents that this vesicle caused. And the answer for changing in this variable are no, this variable wasn't changed by pressure. The M was changed. We see that if the mean was more or less here before, now it was shifted to this mean. So the M is smaller. And now what's caused it? Lower N, lower P, P probability, and number of active zones. Using the 3 equations and 2 variables that are unknown, we could calculate the N and the P, and the general conclusion I will show in the last slide. Just something very, very interesting that we saw in the way was that in the low-yield synapses, these ones that I mentioned before that they have this spontaneous activity, we could see that under pressure. This is the distribution of the evoked potentials, and this is the distribution of the minis, or spontaneous activity, which is usually the same size like this one. The peak was expected to be in the same place. And what we see here, to people that following this level of analysis of synaptic transmission say something about desynchronization. We could see similar effect using strontium that causes breaking down of the synaptic potential into small parts, but is absolutely very different from spontaneous, normal spontaneous EPSCs. So this clue over here, together with experiments that I didn't mention, dealing with the possibility to compensate for the effect of pressure using calcium or elevated calcium level, actually pointed to the possibility that the changes that we'll see in the synapses were due to some changes in calcium entrance to the presynaptic terminal. Additional data that I will skip today that showing increased delay, also delay of the synaptic event from the time that the action potential arrived to the terminal, also indicate that something in the presynaptic side was changed. So just to conclude, back into this neuromuscular junction, what was changed here? There was no change in the quantal size. Each vesicle apparently contained the same amount of neurotransmitter, and the same number of receptors apparently responded there at the postsynaptic side. The quantal content, average number of vesicles was decreased. Decrease in the number of active zones that were active. They are still there, but they are not active. And the probability was changed depending on the type of synapses. It was more pronounced in the low-yield synapses. It was less clear that it was changed in the high probability or high-yield synapses. There it looks more like the N was the only variable that changed. And this spontaneous activity with asynchronization of the release push a little bit to some desynchronization in the presynaptic side, and the calcium experiments that suggest that this effect may be due to changes or most of it due to changes in the entrance of calcium to the presynaptic terminal. And I excluded the thank you slide just because the people were many. So first of all, to all the students that were in the lab and around at the time of these studies, because without the discussions and the excitement and the support from all the students around, it wouldn't happen. And of course, all of them and all of us were inspired by the enthusiasm of Rami and the encouraging that he always gave us to do the work. So to all these people, thanks a lot. And all the supportive money funds that Rami got obviously helped. And thank you.